Hi, I'm Lauri Tuominen, and today I will tell you about joint work I did together with Mo Alula. He's also here right now. That work I did last year at Nokia Bell Labs. So I'm going to present IMULet, or pronounced AMULet, which is a cloudlet for inertial tracking and localization. So localization is a fundamental technology and one of the cornerstones of physical internet. And localization is also a rather fundamental need for us humans and to intelligent moving agents, like, for example, this delivery robot that delivered food in Milton Keynes in England. Now, even though localization has been researched for decades, there has not yet been a silver bullet to solve the problem entirely. However, there is a broad range of different kinds of arsenal. For example, vision-based solutions, radio, audio, and all kinds of combinations of these, you name it. So the key deal, or the main problem yet to be tackled, is robustification. The future of computing must be spatial, multimodal, multi-layered, and semantic to prevent this from happening. Now, this is the same delivery robot from the previous slide, and this is from last August. And since articles such as this still pop up every now and then, it implies we still have far to go for the technology to be in a robust enough level. So what do we need to do to improve? From all of these possible sensing solutions you see on the brick wall, we will be focusing solely on the inertial category. And that is because inertial is kind of a ground zero from all of these. It's because out of these possibilities, it's the only one that's independent of the environment. For example, with vision, you may have occlusions. With infrared, you may have bad SNR on a sunny day. And for acoustic, there may just be a lot of ambient noise. But inertial sensors, however, are not affected by any of these, which make them rather useful. However, only the signal is not going to get us anywhere. We also need a model to extract the useful information out of the inertial data. So we have to take out our bag of tricks and pull out deep learning. But by deep learning, I guess probably some of you flinched at the buzzword, as it has been popping up nearly everywhere recently. But the choice of deep learning is, however, rather easy to justify when comparing it and traditional handcrafted algorithms, for example, pedestrian dead reckoning. Like, as you can see from the figure, the gap in performance between deep learning, which is the green color, and traditional non-deep learning method is too big to disregard. So deep learning has provided major improvements. So deep learning, is that it? Is that the silver bullet? Well, unfortunately, not quite. We need still a lot of system level innovation for real world applications. And the three key elements that the AMULet incorporates are, firstly, designing ultra low power tags that are compute, energy, and form factor constrained. And secondly, dealing with the fragility of deep learning models, meaning that even though IMU data is independent from environmental variables, the signal distribution can still change quite a lot depending on multiple other variables. For example, different motion profiles, for instance, pedestrian versus a wheeled robot, and sensor location, or where it has been mounted with respect to the robot, like center versus on the side, which affects the centrifugal forces that the sensors observe. and the difference in the sensors themselves. Now, this makes it pretty hard to implement a model that is able to generalize between all of these different variables. And finally, we have that the system must be configurable and scalable. Now, next we will go quickly to the actual architecture of the IMULet neural network. It's partitioned to two blocks. The first part is run on the ultra-low power tag, and the second part is run on edge cloud. The first block is relatively light part of the entire model, and it takes in the 9 degrees of freedom IMU signal and runs it through a series of convolutional layers and outputs a vector or a tensor with reduced dimensionality. And this is done on the tag, as the compressed representation significantly reduces the amount of data to be transmitted to the cloud compared to just raw inertial signals. And the compression factor can range from 2 to more than 10, and it can be varied to suit the system needs. The second part is run on the edge cloud, where the tag transmits the compressed vectors. Now, this section is significantly larger in terms of computation, and it does most of the heavy lifting, but it doesn't matter thanks to offloading. There's no constraint on power consumption on the cloud. Now, the compressed representation of the IMU data is fed through a recurrent neural network stack consisting of LSTM layers, which are these one flavor of recurrent neural networks. The LSTM stack acts as kind of a memory of our model, which captures the current and the past states of the moving agent. For example, variables like its velocity and direction, which can't be directly measured with the inertial sensors. And then the output of the LSTM stack is forwarded through two fully connected layers, which finally spit out our displacement estimate. And we also have this estimates delay line, which reconnects the previous estimates back into the model, which kind of constrains the model output, by which I mean that the model learns that it's not very probable for the estimate to differ drastically from the previous estimates. And here are more concrete visuals on both the power consumption and the performance and the configurability on the tag side. First, we have measurements of the power or energy consumption of one forward pass in the convolutional neural network block that's on the tag side. And it's measured with a Jetson Nano, which is a small single board computer. And as we can see, we're talking about millijoules for one forward pass, which means that the total power consumption is going to be order of tens of milliwatts. So all good so far. And here we have the 95th percentile localization error as a function of convolutional compression factor. For instance, around 12 centimeter 95th percentile localization error can be traded off for a 11 times reduction in transmitted signal. Now, one aspect I have not yet discussed is the notion on latent space tracking and the adaptation in the model. This refers to the ability to tune the model such that the neural network is able to deal with IMU data from different distributions, that is, adapting to, for example, different motion profiles and sensor placements. We tackle this problem with a method known as domain alignment, which essentially is to enforce the neural network to align the data from different domains to a single clustered distribution such that the IMU signals are mapped to domain invariant feature vectors. The visualization on the bottom left may give some clarity to the aligning that's happening inside the model. And due to the alignment, these models also perform better on completely unseen domains. And furthermore, the model which has learned to align data from certain domains can be used to detect anomalous inertial signals. The right figure shows a visualization of the domain invariant feature space or latent space tracking and anomaly detection. It shows the Wasserstein distances, which are kind of distribution similarity scores between 6 unique domains from D1 to D6. Now, here a model previously adapted on domains D1 to D5 is given an unseen inertial signal from a different domain, D6. And we can see that the differences between the unseen domain and the others is a lot greater than between the original 5. Now, we can track the deep latent space and utilize this information such that when the model encounters anomalous inertial signals not seen during training, it can be detected and model adaptation can be initiated. Now, combining the partition model, the compression, and the domain adaptation together has given us promising preliminary results. Here we have a CDF and the average error as a function of time for both position and the heading for a 20-second long navigation sequence. So we can see that the distance error after 20 seconds is on average approximately half a meter, and the heading error is at approximately 10 degrees. But for more details, you will have to check out the paper. So in summary, IMULet is a cloudlet for inertial tracking powered by deep learning combined with edge computing and hooks for efficiency and generalizability. And it is a key component towards infrastructureless localization. And here is also a photo of our in-house data collection robot. All right, thank you.